Hello and welcome to this presentation, The State of Fortran 2021. I'd like to start off by thanking the conference organisers for this invitation. My name is Laurence Kedward. I'm a researcher at the University of Bristol in the UK, where I use Fortran mainly for computational fluid dynamics and the related utilities around that. Much of this presentation today is derived from a paper currently undergoing revisions for submission, and so I'd like to acknowledge my co-authors on that paper for their work on that paper and for this presentation as listed here. In this presentation, I'd like to kickstart with a brief explanation of why we use Fortran, followed by a discussion of some of its shortcomings in its ecosystem that have developed over the years. And this will lead us on to the history and motivation for forming the fortran-lang community and its various projects. And finally, I'll finish with a brief introduction to some of the fortran-lang open source software projects as well. Now, Fortran was the first high-level programming language and was developed in the mid-1950s at IBM by a team led by John Backus. Here with the main goal of easing the burden on scientists and engineers when implementing their various mathematical formulas computationally, hence the name Fortran Formula Translator. Fortran was pioneering in many senses, not only being the first high-level programming language, but it is widely accepted as the first optimized and cross-platform language, mainly driven by its popularity and rapid adoption by hardware manufacturers at the time. And consequently, many computationally intensive scientific applications and libraries picked up Fortran as their main implementation language. Importantly, the Fortran language has been under continued development over its 60 years, having been through many language revisions and updates, where the latest standard was released in 2018. And so this leads us on to the first section in this presentation, which is to ask why use a 60-year-old programming language in the 21st century? Or more specifically, what makes Fortran an effective for high-performance numerical computing in the current day and age? Now, the first reason we'd like to argue for using Fortran is the high level of abstraction it provides while also being highly performant. Perhaps first and foremost that sets it apart from other languages is its strongly array-orientated style. So this means it includes multi-dimensional arrays as part of the core language, along with an expressive syntax for performing array slicing. It has strong guarantees around the non-aliasing of arguments, and it provides elemental procedures for trivially defining map-type operations. And so altogether, this means that compilers can generate very highly optimized machine code from the array operations that can be expressed in the language. And so this strong support for arrays at the language level is really fundamentally useful for scientific and numerical computing. Similarly, as a strongly and statically typed language, Fortran inherently protects against common programming pitfalls with meaningful compile time errors and no runtime penalty. By example, the ability to use dynamically allocated arrays without pointers and without risk of memory leaks provides an important source of robustness and safety without any added mental burden to the programmer. Finally, Fortran has a long-standing support for parallel programming through a variety of paradigms, and indeed you will have heard it said that much of the time spent on the largest parallel machines in the world is taken up by Fortran applications. The second reason we argue for using Fortran are the strong guarantees of stability and reliability offered by the language. Fortran compilers must strictly adhere to the Fortran standard, which remains largely backwards compatible with previous language standards while still supporting modern features of the language. This is important in not breaking existing applications and libraries, of which there are many and some of which are very large. And importantly, this means that you can have confidence in using a Fortran library that was written some years ago, but you can also have confidence that your own code will compile and run many years from now. And the same cannot be said of many other newer languages where the development of the language is much faster paced. Now, at the same time, this does not prevent compilers from exploiting modern hardware improvements, since the language is designed to sit at an abstraction level agnostic to the specifics of the underlying hardware. Finally, the third reason we argue for using Fortran is its maturity, and this is most obvious in the number of freely available Fortran compilers, all of which are under active development. And two of these target the modern LLVM compiler and infrastructure for code generation. As mentioned previously, there is a large ecosystem of existing libraries written in Fortran for numerical and scientific purposes, and these codes have been extensively verified, tested, and optimized. Finally, Fortran is incorporated into a number of other well-established standards, notably those targeting parallel execution, such as MPI, OpenMP, and OpenACC. And so to summarize, there are many reasons that make Fortran an effective tool for high-performance computing in this era. Notably, it's easy to learn syntax that provides a high level of abstraction while maintaining very high performance. The inherent stability and longevity that the language provides, which has produced a burgeoning ecosystem of libraries and applications. And finally, the maturity of the language, which is supported by a wide variety of high-quality compilers. And so this leads to the second part of this presentation, where I'll discuss some of the history of the Fortran-Lang community, and I'll start off with recognizing some of the shortcomings in the Fortran ecosystem. So it's important to accept that in certain areas, the ecosystem and tooling around Fortran has really stagnated when compared to that of other modern programming languages. First, it has no standard library for achieving general-purpose programming tasks such as string handling and other operations, and this makes these tasks difficult and also duplicates effort. Second, building and distributing Fortran software is difficult, and this presents a high barrier to entry and discourages the reuse of existing software. And this is in particular compared to other languages which have dedicated package managers for this task. Third, Fortran has no community-maintained compiler that allows the prototyping of new features and developing of new tooling around it. And this is really important for developing the ecosystem and the tooling around Fortran beyond what is supported by existing compilers. And finally, Fortran has no prominent dedicated website, which is really important for new users to discover and learn Fortran. Now, a lot of these shortcomings were identified and discussed on Twitter in August of 2019 between Andrei Sertic, Milan Churchik, and Jacob Williams, where they really identified these perceived shortcomings in the Fortran ecosystem and exposed a desire to change this within the community. Now, a few months later, in October of 2019, Andrei created a GitHub repository for soliciting feedback and proposals directly from the community to bring to the Standards Committee. Now, the workflow for this is quite straightforward. Anyone can create a new issue in the repository to propose additions or modifications to the Fortran standard. And then anyone can then comment on this proposal to discuss it and evolve it openly. And finally, if some kind of consensus is agreed within those discussions, then members can collaboratively and openly draft a formal proposal to submit to the Fortran Standards Committee on the same GitHub repository. And so when this repository was started, there was a lot of activity. A lot of people were very interested in improving the Fortran language and ecosystem. And so there have been over 90 contributors to the discussions in that repository. And among those discussions, 8 proposals have already been formally drafted and submitted as a result of that. Now, in November of 2019, it became clear that many of the proposals to the repository were for more intrinsics, and specifically intrinsics with a much wider scope, for example, performing string handling, file system access, sorting algorithms, and various mathematical routines. And so in November, Milan proposed to start a separate standard library project in response to the requests for these new intrinsic functions. And indeed, in December of 2019, the standard library repository was started under the fortran-lang namespace on GitHub. Now, around the same time, it became clear that there were a couple of proposals on this repository that were asking for a dedicated Fortran package manager and build system. And here the motivation, as I alluded to earlier, is very much to improve the ease of use for new and existing users to compile Fortran projects and also depend on existing Fortran libraries as dependencies. And so this is to create an interoperable ecosystem of high-quality Fortran libraries, and ideally to do all of this with some kind of common front end. And so in January of 2020, the Fortran Package Manager project was started on GitHub under the fortran-lang namespace. A few months later, in April of 2020, Milan launched a new modern website for Fortran at fortran-lang.org. And a month later, we applied for a free discourse instance as well. Now, the fortran-lang.org is intended to be a central community-maintained website for Fortran, where we provide a list of resources and information for new and existing users of Fortran. And so the website is open source. Anyone can suggest improvements or additions to the website. And I do encourage you to have a look and make your own suggestions if you're interested in that. And so currently the website has a list of compilers and community projects, a list of tutorials and learning resources for learning Fortran. We publish a monthly newsletter detailing all of our activity within the Fortran-Lang community, but also wide activity within the wider Fortran spaces. We have a package index for listing common Fortran libraries and programs, and Fortran-Lang is now within the top 2 when you search on most search engines for Fortran. Similarly, we have the Fortran-Lang discourse, which is intended to be a modern, friendly forum and welcoming to all abilities. The forum accepts markdown formatting. In particular, it allows you to format code very nicely, which is really useful for sharing code. And it is moderated to ensure a friendly and respectful discussion. And so we have around over 450 registered users, and we're topping 100,000 page views per month. And so I do encourage you to have a look at this discourse group. There's lots of really interesting discussions going on there, and I certainly learn something new about Fortran every time I visit. Now, as I've mentioned, all of the Fortran-Lang projects are open source, and they are kind of stored on our GitHub organization, which you can see here. And this means that all of our projects can be developed openly and collaboratively using the Git version control system. And this means that anyone can get involved and contribute to the discussions, to code and to reviewing code. And all of our projects are open source under permissive licenses. And so to date, we have over 180 contributors to code and discussions on our GitHub projects. Now, as part of our open source endeavors, we applied to the Google Summer of Code program this summer. So the Google Summer of Code is an international program by Google to fund students for a 10-week project during the summer. And so at the beginning of this year, fortran-lang applied to be a new organization, and we were accepted, and we were given 6 student slots for this summer just gone. And we had a number of students working on our projects. So we had 3 students working on the Fortran compiler by Andre. With Andre, we had 2 students working on the standard library and 1 student working on the Fortran package manager. And so this was a really great opportunity to reach out to the community and also support students and get some really interesting projects done on our fortran-lang repositories. And so if you want to learn more about what I've just spoken about the fortran-lang community, then I do encourage you to read this paper that's been submitted to the ACM Fortran forum, and you can access the preprint via this link. And again, the contents of this presentation will be in a State of Fortran paper coming soon. And so in the remainder of this presentation, I'm going to talk a little bit more about the Fortran Standard Library and the Fortran Package Manager projects, which are really the core projects from the Fortran-Lang community. And then after that, I'll finish with a short demonstration of them both. So the Fortran Standard Library project is aimed to develop and provide a community-driven standard library for Fortran. And indeed, as I've alluded to, this is to provide a set of functions with wider scope than is provided by the language intrinsics. And so this includes various common algorithms, such as for sorting, various programming utilities, such as string handling, containers, testing, and logging, as well as various special mathematical routines that are commonly required. And so this project is open source under the MIT license. It's available on GitHub. And I do encourage you to view the current API, which you can access at this web address, stdlib.fortran-lang.org, to see what's already going on, what's already available in the library, but also to view the GitHub page to see what's being developed and see how you can get involved with that if you're interested. So we currently have 34 code committers and over nearly 100 contributors to the discussions. The standard library has 18 modules, 7 derived types, and 119 procedures in total. And these are the modules as listed here. So we have a number of modules for performing common string handling tasks, such as managing character sets and allowing you to form arrays of strings. We have a number of common programming utilities, such as manipulating bit set types, managing errors, performing common I/O tasks, logging information, and also sorting algorithms. And then we have a number of modules for providing common mathematical functions, such as manipulating matrices, performing numerical quadrature, statistics, and random number generation. So the Fortran Standard Library, all that it requires is a Fortran compiler that supports the 2008 Fortran standard, and CMake and the FIP preprocessor, which is a Python script. And the FIP preprocessor is required just to perform an automatic generation of subroutines for all combinations of ranks, types, and kinds. And so this provides some form of generic interface for the routines in the standard library. Now, the Fortran standard library is supported on these three major platforms with both the GNU and also Intel compiler suites. And these specific platforms listed here are tested automatically on every single commit to the repository. So now I'll talk a little bit more about the Fortran Package Manager project. Again, this is open source under the MIT license, and you can see it available on GitHub here. And this is intended to be a Fortran-specific build system and package manager to really reduce the learning curve for starting new Fortran projects, as well as reusing and depending on existing Fortran libraries. So the Fortran Package Manager is still quite new in development, but it's already very capable. So it can scan module and submodule dependencies and build a wide variety of different project structures. It supports Fortran and C sources and allows incremental and parallel builds to speed things up. And Fortran-compatible libraries can be easily specified as project dependencies, and in this case, FPM will automatically download and incorporate the dependency into the local project build and handle all of the compilation of that dependency for you. And so currently there are over 170 FPM compatible packages available on GitHub and GitLab, and so the ecosystem is growing quickly. So I'll briefly talk about the layout of an FPM project. As shown here, we can see that we have this manifest file, fpm.toml, and this just describes or contains the various metadata to describe the project to FPM. And so very little is really required in this file, because FPM can typically scan and find all of your source files automatically if you follow the default project layouts, which is shown here. So you have a source folder, an application folder, an examples folder, and a test folder. And based on this structure, FPM can scan your project and find all of the sources automatically. Now, the project manifest is also where you would specify third-party libraries as well as dependencies, and we'll see an example of that later in the presentation. So I'll just finish with how you can install FPM. There are many different ways. You can use Conda, you can use MSys2 if you're on Windows, you can use SPAC, you can use Brew on Mac OS, or you can clone the repository directly and build it from source. And so in the remainder of the presentation today, I'm going to give a demonstration of using the FPM and also how we can use FPM with the Fortran standard library as well. Okay, so in this last part of the presentation, I'm going to demonstrate FPM, the Fortran Package Manager, as well as using part of the Fortran standard library within that. So there's lots of different ways of installing FPM. You can read more about it at this web address. You can see that you can download binaries, binary executables here for Linux, Mac OS, and Windows, or you can kind of compile it from a single source file. You can install it through Conda, you can install it through the MSys2 system, through SPAC, or you can build it from scratch following these instructions down here. So what we're going to do today is we're going to install it from MSys2. Now, MSys2 is just a platform on Windows for providing a Unix-like interface with a package manager, and it makes things quite simple for developing software. And so that's what we're going to use in this demonstration. But importantly, you don't need MSys2 to use FPM. You can use it without it by downloading binaries. So the first thing we're going to do is we're going to open up an MSys2 console, which just looks something like this. And we're going to install things that we need. So to install things with MSys2, we can use the pacman package manager. And we're going to install gfortran, which is this first package, gcc-fortran. We're going to install FPM, which is the package name that you can see here. And then we're also going to install GNU plots to do some plotting later on. So we can check what version of gfortran we have. So we have gfortran 10.3 for the MSys project. And then we can also check what version of FPM we have. We have FPM 0.4.0, and we can see that that's the most recent version that's been officially released. So that's good. We've got everything installed. So there's a number of things we can do with FPM. The first thing we can do is just, if we type FPM, we can see a summary of the things that we can do and some of the commands we can do. So we can build projects, we can display help, we can create new projects, run projects, test them, update their dependencies, or even install it. So the first thing we're going to do is we're going to use this new command, fpm new, to create a new fortran package in the current directory. So if we type fpm help new, we can find out more information about how this command works. So we can type fpm new, and then we give it a directory name, a project name, and then we have a few options depending on what we want to put in the project. But we're just going to use the default options and use the default layout that it gives us. But you can read more about this in the documentation there. So we're going to create a new project, fpm new. We'll just call our project demo. And what we can see is it's created a directory demo, and it's created some subdirectories, and it's also initialized it as a Git repository. So if we open up our Windows Explorer, we can see that we have this new folder, and if we open it up, we've got a number of things in it. It's given us a README, an empty README document that we can see. It's given us this fpm.toml file, which is the manifest file. This contains all the information about our project, and we'll look at that in more detail. And then we have an application folder, which just contains the executable programs, a source folder, which is going to contain our library modules, and then the test folder, which is going to contain any tests that we want to run. And so when we use the fpm new command, it creates everything in such a way that the project is all there and it's all ready to go. So we can immediately build this project. So we can use the build command, fpm build, to build the project. And we can see that it's calling gfortran with a number of options, and it's compiling the source code from our project. And if we look into our Explorer, we can see that we have this new folder, build, and this is going to contain all of the build artifacts and the executables. And we don't really need to worry about what's in this folder, but we can just explore it to see that we have our object files, our module files, and also our executable. But we really don't need to worry about what's in the build folder, because FPM gives us a way of running and executing our program. So if we do fpm run, then it will execute the application. So let's have a look at what we have now in this demonstration project. So if I open up it up in any code editor, we can see our folder structure, and if we open up the application folder, we can see we have this very simple app that uses the demo module, calls say hello. And if we open up our source directory, then we can see we have our library module demo, and then the routine say hello, and that's what's been executed here. And then we've also have this default test, so if we run fpm test, then it will also execute this test as well. So these are just the three simplest commands: fpm build, fpm run, and fpm test. Now, if we modify one of these files and then call fpm run again, then it will automatically detect that we've changed the file, and it will rebuild the file and then execute it. But then if we do fpm run again, then it will just execute it. And so we don't have to run fpm build all the time if we are changing our source files. We can go straight to fpm run. So if we now look at the fpm.toml file, this is the manifest file that was mentioned earlier in the presentation, and really it just contains a very small amount of information required to describe our project, really. So we have the name of the project, the version, the license that it's distributed under, the name and contact details of the author, and then the copyright information. And then we have a few extra fields here. These fields aren't strictly necessary, but the first field, these three fields tell FPM to automatically search for executables, tests, and examples. And then this option just tells FPM not to install a library when we call the fpm install command. So we don't really need these for this project, so I'm just going to delete them for the moment. And also in this project, we're only going to be creating an application, and so we don't need the source or the test directories, and so I'm going to delete them as well for this project. But in general, your project will have a library in the source folder and hopefully some tests in the test folder. So in this example, we're going to create a very simple application, and we're going to use a number of third-party libraries in order to do that. So what we're going to do is we're going to read a CSV file. So I have this emissions.csv file that just contains some data that we're going to read in and manipulate. And so the first thing we're going to do is we're going to read in the data from the CSV file. And so to do this, we can use an existing library to do this. So we can use a Fortran CSV library. So I'm going to use this one here, Fortran CSV module, and we can read more about it here, but importantly, we can add it to our fpm.toml file like so. So if I copy this, and I'm going to add it to the toml file, and we can see that we've got that dependency in there. And then to use this dependency, we can add the use clause to our main application, and we're going to use specifically a derived type called CSV file, and that will give us everything we need to read from this folder. So I'm just going to add some declarations now that we'll be using. And to read the data from the file, it's really straightforward. All we need to do is declare an object f of the type CSV file that we've imported from the CSV module, which is what this is providing for us. And then we call f%read, and we give it the file name. We're going to have one header row, and then we're going to read the first, second, and third columns into these arrays that we've declared earlier. And so just to check that that works, I'm going to print out the first 10 lines from that module to check that it's worked. So if we go back to the terminal and we do fpm build, we can see that it's now fetching that dependency, and it's going to build those the extra files that came from that dependency. So it's fetched the Fortran CSV module from the GitHub page, and then it's compiled its objects and incorporated it into our project. And then if we do FPM run, we can see that it is going to run that program, and it's going to print out the first 10 items from that CSV file. And if we quickly peek into that CSV file, we can see that that's what the first 10 items do look like. And so with very little code, we've very quickly been able to read a file and print out the data just using an existing dependency. So the next thing we're going to do is we're going to add the Fortran standard library, and we're going to perform some sorting on this data. So if we go to this web address, fortran-lang/stdlib on GitHub, then we can read all about the Fortran standard library. And if we go to build with FPM, then we can see that we can add this to our TOML file to get access to the standard library. So I'm going to add that in here. And then what we want to do is we're going to sort this data, sort the countries list based on the emissions that are in this data. So the first thing I'm going to do before we sort the data is I'm going to just select, filter out the data based on year. So I'm just going to filter it to select the most recent year. And I'm just using the pack intrinsic function to do that. So let's just check that that works. And so yes, we can see that we're now printing out a filtered list of the first 10 countries, now in alphabetical order, just from the most recent data. So we're going to use the sorting algorithms from the standard library. So if we go to the standard library documentation, which is at this address, which you can find at this address, and then if we go to modules, and then we'll go to the sorting module, we can read the documentation for the various options, and we're going to use this sort index function, which is going to sort it's going to provide us with the indices that sort the array as well as sorting it for us. And so this is a very straightforward function to use. So we've added stdlib, we've added the standard library to our manifest file, so now we can add it to our imports. So we can add a line here. So we're going to use the standard library sorting module, and we're going to use the sort index function. And we also need this int size parameter for our array of indices, which is this type here, integer of int size. So we'll add the array of sorted integers to our array declarations, and we'll add the code to sort it. So we will allocate an array of indices. So this is going to be the array that contains the sorted indices, and we will call the sort index function. So we're going to sort based on the emissions. We're going to store the data into the store the indices into isort, and then we're going to sort in reverse order because we want to see the top 10 countries for emissions from this data file. And then once we've got the indices, then we can sort the countries based on the indices, and then we'll print them out again. So let's see if that will work. And so you can see we're fetching the standard library from Git, and we're compiling those extra modules. And then we're going to run the code, and we can see we've now got a sorted list of the countries with the sorted by emissions, and it's showing us the top 10 countries based on the emissions data in that data set. So this is really nice. We've been able to use this very powerful sorting function from the standard library, following the documentation that we have here very easily, just by fetching it, adding it to our TOML file, and then running, and we've been able to exploit that very nicely. So the last thing we're going to do in this demonstration is going to use one last module, one last dependency called OGPF, and this is a module that will allow us to use GNU plot to do some plotting. So again, this is available on GitHub, and we can see that it allows us to do some nice plotting capabilities. So we're going to, once again, we're going to add this to our TOML file. And then when we go into our application, we just need to use OGPF, and then we're going to be using this GPF type. And this is going to allow us to instantiate an object GP, which will allow us to perform some plotting. So what we're going to do is we're going to plot, we're now going to just plot the data for our single country in time. So we're going to filter the data again. We're going to select just a single country from the data, and then we can use the GP%plot type-bound procedure, and we're just going to plot the emissions against the years. And we can also add some labels to our axes as well, just to clean that up. So once again, it's fetching that dependency, it's building all the extra modules, and then it runs, and we can see we're now plotting the emissions data for one country against time very easily. And so that was really quickly. We've not written a very significant amount of code, but we've been able to do quite a lot. And so the point of this demonstration isn't to show that we can read CSV files, sort the data, and do some plotting. We can do all of those things, but importantly, we've been able to do all of these things by composing existing libraries of code together, and by using them up here, we can reuse code that's been written by others and exploit it so that we can be more productive and do less rework ourselves by exploiting existing code. And so we've ended up writing less than 50 lines of code here, but we can do a lot with that just by reusing these modules. So I do encourage you to try out FPM, which you can learn more about on the website here. And you can also get involved in contributing to the project. It's very active, it's open source. You can see we have 20 code contributors already, and we're always looking for people to help out. So if you're interested in getting involved, then do visit the GitHub page. You can browse the issues, look at some of the open pull requests, and give us feedback on how you find using FPM. And similarly with the standard library, you can view it on GitHub. You can see the open issues to see what's being discussed and planned. You can see what's being worked on in the pull requests. You can have a look at the existing capability in the online documentation here, which is all automatically generated. And you can also learn more about it from the README. So I do encourage you to get involved and try out these projects, because we're always looking for feedback to hear what people think of these projects, and also to get more people involved in them to push them forward and develop them further.